Hi, it's Mr Mac, and we're going to be looking at sound. Well, not looking at, hearing sound. And you might notice I've got expressions of Chewy and all sorts of different sounds that he makes. I could try some, but I think I just need a bit of coffee first. You matter. Now I can say the Chewy sound, and it actually works well. Today we're going to be listening to sounds, but also discovering the beats that occur when you have two frequencies that are just not quite right, and the Doppler effect.
Welcome to Mr. Mac's Physics channel. He can explain things really well and is a lot of fun to watch.
I think I strained my voice on that last one. So we're looking at sound waves in Year 11 Physics. Here are the NISA outcomes. Now, note the bottom one which says analyse qualitatively and quantitatively the relationships of the wave nature of sound to explain beats, and there's a formula there, and the Doppler effect, and there's a formula there. So we're going to look at beats and the Doppler effect in more. The inquiry question is, what evidence suggests that sound is a mechanical wave? We're learning to describe the relationships between characteristics of sound by their wave properties. And we'll be able to analyse qualitatively and quantitatively the wave nature of sound to explain beats and the Doppler effect. So the nature of sound waves. Speed of sound in 20 degrees Celsius dry air is approximately 343.2 meters per second. Sound waves are longitudinal waves. From the data sheet, we round that number to 340 meters per second. And here's a diagram showing how there is increased pressure and decreased pressure in the atmosphere. And it's the increased pressure that is symbolized by the dots being really close together. And as the propagation of the sound goes from left to right in this diagram, the motion of the air molecules that are associated with the sound vibrate also left to right, but they don't progress in the same direction as the propagation of the sound. So how do we model sound waves? I wonder how you would do that if you had some friends that you just wanted to model it. Perhaps you might stand in a line and see if you could have some sort of disturbance that gets passed along the line. Well, this picture that we see here tries to show a little bit about modelling sound waves. And the higher the amplitude of the longitudinal waves or compression waves, the louder the sound. And loudness is measured in decibels. And here's a picture of my class coming in for a physics lesson. You notice they're coming in faster and faster. And a wave. Whenever I said the word wave in one class, the back row would instantly go into a Mexican wave, similar to this animation. Let's have a look at worked example 1, which has to do with beats. And there's an animation there from Penn State University, which I think is very, very clever. Here's the question. A tuning fork with a frequency of 256 Hz is played simultaneously with a musical instrument with a frequency of 254 Hz. What's the frequency of the beats heard? Now, beats are an increase and decrease in volume that we apparently hear due to two sources not being the same frequency. They may be close, but not the same. And they form constructive and destructive superposition, as shown in this animation. So here's the data. The first frequency is 256, the second is 254 Hz, and we want to find the frequency of the beats. Here's the formula from the formula sheet. The frequency of a beat equals the absolute value of F2 minus F1. We substitute, so 254 minus 256, absolute value of that is 2 Hz. So the frequency of the beats you could actually hear it 2 times every second. Let's have a look at a second example, which is tuning a guitar. Now, I play guitar, and I started learning on classical guitar with the standard tuning, E, A, D, G, B, E. But it requires tuning the second string to the A2 note. But if you only have a tuning fork, and when I first started playing guitar, I only had a tuning fork with a frequency of 440 Hertz. And the two frequencies are too far apart to produce beats. Well, you know that the string is close to the right note, but it's not quite there. Now, when you play the fourth harmonic and the tuning fork at the same time, you notice that there's a beat of 6 Hertz. What do we do? And what is the frequency of the mistuned second string? Well, here's the data. F1 is 440 Hertz. That's the frequency of the tuning fork. The beats that we hear is 6 Hertz, and we want to find out the frequency of the string. So here's the same formula, but this time we substitute F beat is 6, F2 minus 440, and we actually have two answers. Two possible ways. When we're dealing with absolute values, we may end up with two equations. F2 could be 440 minus 6 or 440 plus 6. So we have a choice. Is it 434 or 446 Hertz? We can check that by actually tightening the string slightly to see whether the beat frequency increases or decreases. And that's how we tune guitars. Here's another worked example taken from the central west of New South Wales, where an XPT is going through a level crossing. That's to do with the Doppler effect. A person is standing next to the level crossing and observes a train travelling towards the level crossing in a straight track at 72 kilometres per hour. The train driver is pressing the horn, which gives out sound waves at 256 Hertz. Part A, the question is, what is the frequency of the sound that the person hears when the train is travelling towards the observer? There's a part B, what does the person hear when the train is travelling away from the observer? Here's the data for part A. The speed of sound in air is 340 metres per second. The frequency of the horn is 256 Hertz. The velocity of the observer is 0, standing still. And the velocity of the source, that's the XPT, is 72 kilometres per hour, which is 20 metres per second in SI units. And we need to find the frequency of the sound as it's approaching us. We call that F dash. Here's the formula. It looks complicated, but it's actually quite easy to use. F is simply the frequency of the horn. And we look at the velocity of the wave, the velocity of the observer, and the velocity of the source, and we simply substitute. So here they are, 256 times on the top line 340 plus 0, on the bottom line 340 minus 20. And we get an answer of 272 Hertz to three significant figures, which is a higher pitch sound as the train approaches. So we find out that the sound of the apparent sound of the pitch as the train is moving away. First of all, the difference between the pitch of the horn and what we hear as it's approaching is 272 minus 256 Hertz, which is 16 Hertz. Quite a notable, significant difference in pitch. As the train passes the observer, the person then hears a lower pitch as the train moves away. So we subtract 256, that's the train horn, minus 16 Hertz, and we end up with 240 Hertz, again to three significant figures, which is a lower pitch as the train goes away. What does that sound like? So we've seen in Year 11 physics, beats, when we have two frequencies that are not quite the same, and the Doppler effect. And we've had a look at some trains going past really fast and what they sound like. I'm Mr Mac. Thanks for watching.